Our special guest today is Gene Humphreys of the University of Oregon at Eugene. Gene has a very interesting career that's sort of non-traditional and kind of an inspiration. You should ask him about the details later if you're interested, but he taught community college for a while and then attended the University of California, Riverside for a bachelor's and then a master's degree, and then started his PhD at Caltech, where he was a contemporary of Owen Steve Grant, who regrettably couldn't join us today. Gene then joined the University of Oregon as an assistant associate and full professor, and he now holds emeritus status. Gene's work really has a very eclectic flavor, and he's worked on a number of aspects of the solid Earth system from a geological or a geologist's perspective, from a seismologist's perspective, and also from a numerical point of view. And he's worked on fault strength, the partitioning of slip rates. He's worked with his students, of which there are numerous, on anisotropic thermal conductivity. And I think much of his work speaks to how we can link mantle dynamics to continental tectonics on different scales, issues such as delamination, modification of the lithosphere, subduction dynamics, and what he's going to be talking to us today, flood basalts and other thermomagmatic systems. Gene has won numerous honors. He's a fellow of GSA, a fellow of AGU, and he's just a really great guy and one of my favorite geologists to chat to. I had a chance to spend 12 days in the Grand Canyon with him on a GSA field trip, which was sort of both too short and too long in some way. But it's my great pleasure to welcome Gene.
I think you just called me a geologist. No. No, when I was an undergraduate, geology sounded very interesting. I was going to head that way, but I had to learn too many words. And I ended up in physics and geophysics. Anyway, you sort of see a title slide here. And, you know, I've talked about what I call the CRB, the only acronym I'll really use in this, but the Columbia River basalts, the CRB. And I find I've been so deep into it. I talk about it, and I think people in the audience, I get the sense of blah, blah, blah. So I've tried to rearrange things more towards what I think are some of the interesting results from this. But anyway, you kind of see it. I'll go through some of these results. I'll lead to those as I go, but I'll start with them now. And one of the main points of all this is most of what has happened in my efforts with the CRBs has surprised me about how the Earth works. First of all, it looks like plumes can lift slabs. We'll see that very shortly. And pre-existing instabilities in the lithosphere dominate what happened here. The plume is important in the story, but that's most of the energy, most of the driving is actually in lithospheric instabilities. I'll go through 3 of those. Okay, and I'm going to tell you that I think flat slab delaminated, flat oceanic slab delaminated that was left there, and the continental lithosphere for all this activity stayed there and didn't come off. I think for a lot of what happens, wrong button, there we go. For a lot of what happens, I think eclogite is going to be important. So just the dense rock that gets created. And some of this foundering is going to drive crustal flow and rearrange the crust in ways that is interesting. So let me jump into it. I guess there's different plumes around the world. I should say different flood basalts around the world. Just to sort of put the CRB in some perspective. I learned that probably is not a flood basalt, to my surprise. But anyway, a lot of big basalt eruptions usually attributed to plumes. The CRB is the most recent and well-studied of these. We have a lot of remnants of what happened available for our study. That helps a lot. It is one of the smaller ones. But I gotta say, it's smaller, but it's not small. You see the area covered here, almost bigger than the state of Washington. And just the standard view of plumes, I think going back to Mark Richards and people. And you see different hotspot tracks and flood basalts. And the general picture people have is hotspot tracks usually start with a flood basalt. And if you see a flood basalt, there's usually a hotspot track leading away from it. And that has led to this sort of iconic view of what this is all about. A instability from near the core rises. As it rises, the plume head inflates. When it hits the surface of the earth, you have this large mass giving rise to a lot of basalt, and you get a flood basalt. Then as the plate moves away, you get a hotspot track. Okay. Well, the model predicts, among other things, no hotspot before the flood basalt. Okay. And there should be pre-eruptive uplift. As this plume ascends to the surface of the earth, it's going to lift the Stegosaurus up before it gets there. Okay. I write down this famous quote from Leo Tolstoy: "All theoretical plumes are happy, but every real plume is unhappy in its own way." Okay. The CRBs are going to be unhappy in their own way. Okay. For instance, first of all, it's happy in that it fits the standard model in that we have a flood basalt, and then we have a hotspot track. Okay, that sounds pretty good. The ways it's unhappy, there's no evidence for pre-eruptive uplift. And then the Climber basalt eruptions got very far off track. They started where you would expect it if you back project Yellowstone, but very quickly it got all the way up to Washington from Nevada. Okay, and as it went north, the volume of eruption increased. Okay, and so the final strong statement is this hotspot was active before the Climber flood basalts. It actually created this large igneous province that accreted to the margin of the Pacific Northwest. So it is not a plume head from the deep mantle. Okay. Well, this is just a standard model, I guess you could think a lot of them, but here's the idea of an ascending plume head. Hasn't gotten to the surface yet, but that buoyancy is lifting the surface up, and you expect this uplift before eruptions. And here are the first eruptions for the CRB, and they came into a basin. Okay, no sign of uplift there at all. Okay, I make the side comment down here. There's kind of a dearth of evidence for pre-eruptive uplift for hotspots around the world, I should say, for flood basalts around the world. So that's interesting. Okay, and just quickly, this first activity down here, Nevada-Oregon border, started at some age, but within just a few 100,000 years, it was already erupting in Washington. So the rapidity of migration is astounding. How did it get there? You know, just a standard model against same model from Baroff showing that 300 kilometers, you know, in these models should take millions of years, 4.5 million years in this case. So I want to go into a brief history of this hotspot to put it in more perspective. There's a slide from Ray Wells, and the idea is Yellowstone that was active off the coast of North America, and then it got overridden by North America. When it was off the coast, it was on, make sure I get the right button here. It was on a spreading center between the Farallon Plate and, you take your choice, cooler resurrection. People argue about what was up there. It doesn't matter. There's a spreading center with a hotspot on it. And it forms these two large igneous provinces. One of them is now subducting under Alaska, the Yakutat large igneous province. But it also created this Silesia province that accretes to the Pacific Northwest. Okay, so the main point here is Silesia was active before the CRBs. Okay, and then what happens? Well, this is a picture from Vic Camp, who's worked a lot on the CRBs, and his view of things is this plume got caught under the slab, very similar to Geist and Richards going back to 93, of the plume being trapped under the slab. And so the plume head, if you want, is this mass of plume accumulating under the slab. And then when the slab breaks or it gets by somehow, when that plume mass hits the surface, you get a flood basalt. That's kind of a standard view now. And there's Vic's picture of that lifting a slab. I sort of asked rhetorically here, could this little plume really do this to a cold slab? Okay, it's just one little spot in the big slab. The slab average is 500 degrees. According to Bill Lehman anyway, this plume is about 100 degrees in excess temperature. It's not a very vigorous plume in that sense. Could it happen? Okay, before I leave this slide, I'll just say, if this is your picture of the plume head coming up from the core mantle boundary, I just want to make it clear, this is not what we envision for the CRBs. Okay, okay, another picture from Vic Camp. What he shows here is this plume flattening, but he shows the magmatism he thinks is associated with it. There isn't much magmatism at this time, but there are adakites along a trend across southern Oregon, which he attributes to the melting of the oceanic crust. They're high potassium magmas that he attributes to the hydration of the mantle above this. And so from a geochemical point of view, it looks like maybe the slab did get flattened out. I also point out that the Juan de Fuca slab has this curious hole in it. We've had thousands of kilometers of subduction since it started, and yet we can't find slab beneath that. Okay, and the plate is subducting towards the northeast. So if you just back project this to Yellowstone times or CRB times, it was down here where we expect Yellowstone to be passing. So we're missing slab here. We also have this extremely large, low velocity structure underneath Oregon. And I don't know of any other structure beneath North America, or actually anywhere else that I know of, where you see things slow down to 200 plus kilometers like that. So this is anomalously slow mantle. Okay, and we also, maybe it's fantasy, but we see little high velocity things down here that look like they could be torn apart slab. So you could make the case, I think certainly got to put it on your list of what you're thinking of, that this little plume actually did hold this slab up and broke through, and then subduction reestablished itself in a more normal kind of way. Okay. I make a side comment here. How did it lift the slab? One way, the natural thing you'd think of is that this is buoyant and it's just holding the slab up. Another interesting thing to think about is that this is hot, breaking apart the slab. This adakite represents the crust being melted and perhaps getting away in some way. You're reducing the weight of the slab. So there's no longer such a negatively buoyant body as you might be imagining. But this is a young slab. I'll come back to that. So it's the mantle buoyancy is, I think, pretty insignificant in this case. It's the crust that holds most of the negative buoyancy. Okay, side comment. That's talking about mantle tomography and people have different backgrounds. I just want to say that if it's more than 1% fast in the mantle, so all the blue stuff here, is cold. That's the only way you can really make it seismically fast. Okay, if it's cold, it was made near the Earth's surface, obviously. So we're really talking about lithosphere. This is lithosphere that has not been in the mantle long enough to warm up. Okay, and I say, if you go west of the old Cretaceous arc, there's not enough North America mantle lithosphere to point to make these structures. So the only thing left is subducted ocean lithosphere. Okay, and you see for comparison, the Juan de Fuca slab. Okay, so all this stuff down here somehow is ocean lithosphere, and the only ocean lithosphere you can point to is subducted parallel plate. Okay, so that's how I'm envisioning that. Okay, back to the CRB. Here are the first eruptions. You see the dikes erupted from, and it's filling the Steens Basin. I'd say no uplift there. Okay, but with time, and here we are 80,000 years later, and the next eruptions, are up here. The next sequence of flows, the Imnaha, they don't fill the basin. Okay, they get dammed down here and flow to the north into Washington. It looks like in 80,000 years, this area has come up and keeping the flows from going south. Okay, and then we just flip through more flows. There's the next flows, again propagating north, and again dammed to the south, and again, and again. You see where the dikes are. Again, you just see the magnetic sequence propagating north. These are the deposits, but you see where the dikes are propagating north, but not to the south. It really looks like you're developing topography under Oregon during this sequence. So a little picture, just to show a cartoon. Here is whatever's going on in the mantle, uplifting eastern Oregon, and the flood basalts are now accumulating up here to the north. Okay, and there's over 1 kilometer of basalt here that couldn't get to the south. Okay, so something like 1.5 kilometers plus or minus of uplift of eastern Oregon. So you got this very one-sided uplift propagating north of both eruptions and uplift. Quick side comment here. I'm not sure how important the propagation of the eruptions are in all this, in that there is real sign of real lithospheric signature propagating north. It looks like they are erupting through the lithosphere some. But by and large, I think the prevailing view now is that most of this basalt comes up to its level of a hydrostatic equilibrium and propagates laterally, like you see in Hawaii, for instance, or something, and erupts outwards lower. So it just can't make it to the surface. It kind of looks that way. So maybe the propagation of magmatism is not such a big deal. The propagation of uplift is pretty indisputable. Okay, and so here's a little cartoon I have from my envisionment of what it looks like if I just blow up this area. The area I've shaded here has been uplifted 1 to 1.5 kilometers, something like that. And I just point out that there's a snake river plain. That's a later structure as Yellowstone continues to load, the crust sinks down. And this very strange bullseye, I'll get to maybe the most fascinating part of the whole story as far as I'm concerned. But that's later, that's at 10 million years. This is more like at 16 million years now. Okay, I'm not going to go through this. I'm just going to say you could take a minimal plume, let's say plus 100 degrees centigrade, excess temperature, 75 kilometers thick flattening, remove 5 kilometers of basalt. How much uplift do you get? And you get something like maybe almost 1 kilometer. You can take a more maximal plume and you get something like 2 kilometers. So within the range of what I can imagine, 1 to 2 kilometers of uplift is predicted. Let's say the uplift of the plume arriving didn't exist. No pre-eruptive uplift. This uplift is being made as the CRBs erupt. So it's a sort of more lithospheric process of uplift in some way, not so much plume buoyancy. Okay. A couple of slides stepping back in time. So what's going to be important is what did the plume hit underneath Eastern Oregon? So the first thing to say is underneath the Pacific Northwest, I will argue strongly for flat slab subduction up to, say, 54 million years ago. Okay, it has all the classic signs of it. During a time of subduction, there is no magmatism, but there's lots of thrust faulting far from the subduction zone. And the typical picture people have for that is down here. The Farallon plate is separating the asthenosphere from North America, no magmatism. The shear tractions are driving thrusting, and it's quite similar to the Rocky Mountains, for instance. At 54 million years, everything changes. This is a big event in Western US as a whole. The famous Western US ignimbrite flare begins, okay, all at once almost. So you see all the volcanic areas. In the Yellowstone area, you see the Absarokas, that's not the hot spot. And you see all sorts of other volcanic activity. And instead of being contractional, it's extensional with these core complexes. So everything changes to just the opposite of what it was. Okay. And the only way to get this magmatism is to not have the flat slab there, so it must be coming off. So you see a little picture of it coming off in some way. Just a blow up of that, but you see one place where the volcanic activity does not exist is in Eastern Oregon and southeastern Washington. So I inferred that's a place where the slab still was. Okay, I'll argue that more as I go, but that's where I'm going with it. Okay, so the slab removed from all this area, and eventually the ignimbrite flare-up propagates south across Nevada. So the slab is coming off everywhere. It'll come off here, you say, 16 million years ago with the CRB. Okay, so now try to relate this picture that I just showed you with the mantle structure. Okay, so I've added a little bit of mantle structure on this. There is Soletia that accreted that caused all this change. But you see in this cross section from north to south, you see this high velocity piece of, I've argued it has to be ocean lithosphere, probably Fairlawn, dangling beneath northeast Oregon. Okay, so there's a wonderful slab. Okay, there's a little bit of craton up in the corner. I'm not going to talk about this. If you're interested, I'd be glad to, but that's another event. Our story here is that. Okay. So I get to the first lithospheric instability of the three I want to talk about, and probably the driving one of most of this, and that is the removal of the Fairlawn slab, which gives rise to the volcanism and the uplift, and more. But at least right here, I'll say, here is the slab delaminating from south to north to give rise to that north propagating uplift. Yellowstone plume flattening beneath it, and there's the uplift above it all. And here's the image of what we see today. Okay, just want to say, for delamination to happen, you need two things. One, you need the delaminating body to be heavy enough, negatively buoyant enough to actually come off. And also you need some means to detach the thing. Okay, and in this case, we have everything we need. We have the oceanic slab, and with Yellowstone being here, we have a lot of melt being released, and so we have basically no strength across that boundary. So it's very easily detached. So in my mind, this is what's giving rise to the north propagating detachment and delamination of the Fairlawn slab. Rolling back, so you see a little cartoon where I've overlaid a little sketch. There's the Yellowstone plume that's come up. Here's where the slab was, and it's been detached and rolled back, and there it is now. Okay. Well, I've argued that there is flat slab beneath Washington as well, and the uplift only propagated that far. So what's going on beneath southeastern Washington? You know, maybe it's almost a side comment, but I'll show a picture. Here's the lithosphere cenosphere boundary map from Alan Levander, and you see the thickness where it's green and yellow goes down considerably thicker than where it's red. On this cross section, you see the lithosphere cenosphere boundary down here, 50 to 60 kilometers. In between these purple lines, in this area, it suddenly steps down to 75 or 80 kilometers. Okay, that's consistent with the slab still being there. And you just look at the surface wave imaging and you see a similar kind of thing. It's fast here, and then you go deeper and it's slow. So it looks like the flat slab is still beneath eastern Washington, southeastern Washington. Okay, so the anatomy of this delamination. Don't know if this is true of all of them. Okay, but the idea is I want to focus now on this area where the detachment is occurring. And if we zoom into that area, here we go. Here's from receiver functions. We've got a well-imaged MOHO. With receiver functions, you see it goes down to 50 kilometers or so. You actually migrate that and you see it going down even a little deeper. But you see this big local downwarp, that map view you see right here. So that's where the crust is suddenly very thick. Okay, which is kind of a surprising thing in this part of the world to see a little blob of thick crust. And in cross section, you see I sort of line these up. Maybe the next figure shows it better, but it's right at that detachment is where we see this crustal thickening. And so here. So to put it together more, we see this south and north propagation of uplifts and volcanism. We see this dangling slab, I would say. And right where it's dangling, we see very thick moho. Now sort of line these up, you see this white line being moho thickness. And then you go north of that and you still see slab underneath Washington. So that's a picture of the slab coming off, I believe. Okay, and one more thing to add to that. Here's where that dangling slab is, the thick crust right here. If you suddenly pull this crust down, well, maybe not even suddenly, if you pull that crust down, that's a large volume that you have to fill with crust. Okay, and we look at the seismic anisotropy in the Pacific Northwest, and there's where the crust is thick, and all the fast directions of the anisotropy in the crust point to that area. It really looks like you flowed the crust towards that downward. Okay, so I guess the point is all these various observations are really painting quite a consistent story of a slab that was left as a fragment underneath Eastern Oregon and part of Washington that during the CRB event delaminated. Okay, but to say a little more, here is the slab. If this is ocean slab, it has basalt on top of it. Okay, as this thing is delaminating, it's going deeper in contact with the Yellowstone. It should eclogize. Okay, so it suddenly turns into quite a bit denser rock. And if I just plot what we calculate for a young ocean mantle lithosphere, we have that down here, and it's negatively buoyant. Okay, but it is positively buoyant by virtue of its depletion. You've taken a lot of basalt out of it. You've removed garnet and iron. It's now compositionally more buoyant. It's thermally negatively buoyant, but because it's a young slab, it's not all that negatively buoyant. And you sort of look at both these and integrate it over the whole slab, it's about neutrally buoyant. Okay, so you usually think of slabs as being very heavy, cold things, but I'm saying here it looks like it's roughly neutral in its buoyancy. However, eclogite, here's just a map of eclogite, and you see as pressure increases or as depth increases, it goes from a little denser than what you expect for mantle to quite a bit denser as you go down. So I think the main driving force for this delamination is actually the eclogite on top of the slab. Okay, well, I think that's kind of interesting. Okay, and furthermore, I think here's maybe an early phase of the delamination as Yellowstone came up, melt detached it, eclogized the lithosphere or the crust, but then you see it's propagating. And I just imagine this little eclogite load propagating along at the same time the detachment is propagating along, and here it is now. Okay, and then I suggest in the mantle that the crust is gone. Okay, I think the next slide may speak to that a little bit. Okay, what happens to oceanic crust on top of the slab? In normal subduction, it seems to go right down with the slab and not detach. Okay, but when I look at evidence around the Western US, a lot of these things are pieces of Farallon slab left behind, and they all seem to be fairly neutrally to, well, I'll say roughly neutrally buoyant. If they were negatively buoyant, they would be gone by now. If we look at this body in particular, now we're looking at mantle anisotropy with SKS. We see no sign of a dense body here. I think what you're seeing is corner flow to Wanda Fuca that dominates. And you also see perhaps in this area where it's very low velocity, the evidence for buoyancy as this thing's trying to flatten out some, perhaps. But the important point is you don't see any evidence of this thing being negatively buoyant and sinking. It just seems to be hanging there. Okay. So I guess I mentioned various things here. Yeah, I guess I said all of that. Stalled slab. I guess some models, you know, Sinti Lee and Ken Wang Ping Chen, I think, have models the slab crust coming off if it gets stalled. There's certainly a shear stress trying to drive that. So that's my sense of what's going on here is the crust is gone. Okay. So back to what delaminated. If this is ocean lithosphere that's coming off, that was underneath Oregon. Here is, hit the right button. Here's the MOHO, and here is the LAB, the lithosphere asthenosphere boundary. It looks like you still have North America lithosphere here. Okay, there's where the slab is still under Washington, but North America lithosphere appears not to have come off. It seemed to have plenty of opportunity to come off, lots of magma around, buoyant asthenosphere. It's still there. Okay, so what is coming off seems to be the ocean lithosphere and only the ocean lithosphere. Okay, so just a general comment here. Delamination has become a very popular thing recently, and I just show various pictures from people, but the idea for almost everybody is the detachment interface is the lower crust because it is low in viscosity, and so it easily detaches there. Not as easily as melt, I would say, but that's the idea, is it detaches there. And you see various models where the lower crust is the detachment zone, here, here, here. And I look at the various places around the world where people have suggested delamination. It's fairly recent. And as far as I know, most of these have had or could have had flat slab beneath them. And I wonder what's coming off if the delamination isn't really pieces of old ocean lithosphere, and that continental mantle lithosphere delamination isn't maybe all as common as people think. Okay, never mind. Oh, I want to say options. I provided a story, but I want to give a couple options to this. I said this is basaltic crust that eclogizes. I don't know if that's true or if it was always eclogite sitting there. It's deep enough. It's in the eclogite stability field. It just has a kinetic barrier to get over. Okay. So I don't know if it was eclogite or basalt to start with. I'm just saying it's eclogite here was detaching and getting denser and denser as it's going down. Okay. The other thing is I showed this slab is continuous, but is it continuous or did it detach here? I don't know. There's an image, a most recent image actually here, and it looks detached. The problem we have, sort of technical thing, is this is where the crust is very thick, and so teleseismic arrivals are very delayed, and they're coming pretty much straight up. We can't really resolve what's going on here very well. Okay, when I look at the surface wave imaging, it looks like the slab may be detached there. Okay, and it very well could be. So I don't know if it's through going or not, just to be more complete and honest about things. Neither one of those changed my conclusions from what I've been saying, but if you're worried about some of the imaging. Okay. The second lithospheric instability is a pretty common one and a pretty simple one. We have weakened the lithosphere, we've uplifted the lithosphere, so we have gravitational forces trying to drive extension, and we have a lack of strength trying to hold it together. So it looks like the crust could easily extend, giving space for the CRB dikes to propagate through the crust. Okay. And if you just look at a map, all these little red lines being sort of schematic dikes, here are the actual map dikes. You notice they're all in the blue areas where they're exposed. There's a lot of dikes that are buried now. Okay, but where they're exposed, you see, 50, 400, 250 meters of extension. And we know there's more than that, but that's at a minimum. Okay, it doesn't take but a dike or two to completely eliminate sigma 1. So we have to keep extending this area if we want the dikes to keep coming in like this. And indeed, on the left-hand side, you see the same picture, all this extension in this area. So I show it extending. In Central Oregon, at the same time, we have rapid shortening. So just kinematically speaking, we have this wedge of crust that seems to be rotating around, escaping this area and compressing that area. Okay. Not dissimilar to what we see today. Now the extension is across Yellowstone. This whole area is rotating, and the shortening is across central Washington. So the scale of everything is opened up. But to start with, it really looks like it was very concentrated right around this event. Okay. On to the third instability, which happened after the CRB, but I want to talk about here on this map of North America, you see the hotspot track. At the very end of the track, you see this strange bullseye. I don't know if you ever noticed it when you look at topography before, but very bizarre little structure. There it is blowing up. And you see this bullseye structure, a ring, a moat, and in the very middle, you see the Wallowa Mountains. Total side comment, but if you ever get to this part of the world, you got to go there. Okay, the Wallowa Mountains are beautiful granitic uplift, flood basalts all around, Hell's Canyon, locally deeper than the Grand Canyon right next door. It's quite a fantastic area to visit. Okay, I call this not the Wallowa Mountains here, but the Wallowa Batholith. Let me say more about that. Oh, I must have removed something. I guess I'll get to it. But I'm sort of labeling this is going to be a Green's function foundering event, a very local little foundering that gives rise to what we're seeing in this bullseye that was put on top of this plateau that was made during the CRB. Amazing. Oh, yeah, I know my logic now. Okay, so here is, I think Davenport et al. Did an active experiment, wrong button again, across in the sacred plane and across where everybody takes the main magma chamber to be for the CRB, which is in the very westernmost Snake River plain. And you see just where the magma chamber is thought to be, you see higher velocities that are taken to be the magma chamber in the lower crust. So that's thought to be the magma chamber for the most of the CRBs. Okay, and it points out this boundary. This is older North America. In fact, some of it's Archean. And from here over is accreted oceanic island ocean terrains that have been accreted on. So not much granite in there. Okay, so here's a map. Here is that suture between old North America and accreted North America. And highlighted here are the few granitic bodies that exist in it, created after accretion. And the main body is the Wallowa Batholith, right there. Okay, and I guess the association between where the batholith is and where the Wallowa Mountains uplift is pretty astounding. Post CRB, which I think I have a slide to show that. Yes. Okay, blow up of that area. But here is a map. Well, first of all, here's just a map of the various CRB flows. I think in purple, you see the basal flow in this area and the various flows on top of it. They were laid down flat. Okay, what you see now is a couple kilometers of relief since 16 million years ago. Okay, the Wallowa Mountains in particular have come up. If you just map view the uplift as best you can, you see this. There's the Wallowa Batholith, the Wallowa Mountains, and you see it's high. On top of the Wallowa Mountains, there is that basal flow, the Imnaha. Okay, you can go just next door. You'll get it throwing a frisbee, probably hit it down here in the bottom of Hell's Canyon. And there is that same flow down at the bottom. Okay, so you see about 2 kilometers of relative elevation here. That is pretty much post CRB. Well, I say we don't really know what that was out there. Okay, so I kind of label this Russian tectonics down here. The idea is probably this granitic body lost its dense root so that it could buoy up as you see. Okay, so the idea is it's not horizontal tectonics and the associated faults that give rise to the uplift. This is deep changes in buoyancy structure giving rise to the uplift. I think which the Russians argued for when plate tectonics was arriving on the scene. Before your time for the most part. Okay, I'm not a geochemist, but here's some geochemistry. And you see basically the strontium to yttrium value is quite often used as a measure of depth of segregation. Did it happen in the garnet stability zone in particular? And the more you get up in this area, you see evidence of a garnet-rich root. And what you're seeing at the surface is rock that is garnet poor. Okay, and you see it also in the rare earth distribution in various Wallowa plutons. Okay, what you see here, I should have mentioned, these are both Sierra Nevada and Peninsula Range in the little dots here, and in the more colorful ones, you see the lavas. The lavas are quite distinctly elevated, this strontium to yttrium ratio, suggesting it really did have a segregation event involving the extraction of a garnet-rich root and the granite left above it. So it has what it needs now for the spectacular uplift that we see. All we have to do is lose that load. Okay. Another interesting thing, I think, is here are the Wallowa Mountains. Here is the Wallowa normal fault. It's bizarre in a lot of ways. I won't go into all of that. But this cross-section shows the strangest thing. There is the Wallowa normal fault, and the hanging wall tilts up towards the mountains. That's backwards of everywhere else I know about. Usually in normal faulting, the hanging wall sinks. I just put an example in here. There are the Grand Tetons, there's Ginny Lake. What always happens is in extension, the hanging wall sags down. That's where the water collects and the rivers, everything right against the mountains. Here, it's dipping up as you approach that fault. How do you get it to go backwards? It's not drag. The wavelength is way too big for that. People don't believe much in drag anymore. The idea is that when the lava root fell out, you need to fill that void with crust, and that crust is flowing in to fill that area, and you got this moat being sucked down by the evacuation of crust. Okay, there's the idea for the moat. Okay, like I say, here's a picture from, this is a picture looking at the lavas at the uplifted ramp, sitting like I mean at the terminal gravity group up. If you ever get to the lavas, head to terminal gravity group up. You'll see the same thing. And have a good beer. So one more thing, here's the anisotropy again. This is a work of Jorge and Rob Clayton. Now I'm showing the lavas, and everything is converging. I would say it's hard to distinguish, but you see both the crustal downwarp was here, and here's the lava where I expect there was a hole beneath it, and you see flow towards both of those. In my imagination, I can kind of separate the two. Maybe that's just wishful thinking, I don't know. But the idea is the crustal anisotropy suggests flow into that hole as well. So kind of putting it all together in a bigger sense, here is the Farallon slab. It's delaminated. The lava batholith and its root has been hanging out for 120, 140 million years, based on the age of the granites. It's always had slab under it. Ever since it accreted, subduction went under it, forming the Idaho batholith. It has not had a chance to disappear into the interior of the earth. It's stuck there being supported by the slab. Okay, now the slab comes off, the root has lost support, and so I'm envisioning that eventually that root falls off. There's the dense root and probably some crust going down with it. Crust will flow into that area and uplift of the batholith itself and subsidence of the moat. So that's my imagination of what's going on here. What do I have? Oh, a couple of summary slides here. So to put all together, in a sense, Yellowstone arrives to the south. It triggers the delamination of flat ocean lithosphere. You see it propagating under. Here is that restite root under the lavas, being supported by the slab. Slab rolls under that root, and now it's allowed to fall off. Okay, it took 5 million years after the CRBs to do that. But that's what I think has happened. And I got almost all of that story are things I did not expect before I started. Okay. So I kind of started with this, but I'll list some of the things I conclude. It looks like the plume in some way lifted the slab, okay, and tore it apart. It was flat ocean lithosphere that destabilized, not continent. Pre-existing lithospheric instabilities are what dominated the activity. Yellowstone may have destabilized it, but it is the foundering of the root and the delamination of the ocean slab that really dominate what's going on, giving structure to it, giving rise to uplift. A lot of this delamination of the slab, the founding of the root, that all depends on eclogite pulling it down more than anything else. And with the crustal foundering of the Wallowa root, you had to have crustal flow into that hole. And we think we see that in the moat and in the anisotropy. Okay, I think that's all I have. Yeah, okay.
Thanks a lot, Gene. Time for questions.
Great talk, Gene. So you mentioned that the oceanic crust, when it dips below 50 kilometers in the northwestern U.S., could turn into eclogite, and that's an important driver of getting the slab down. One of the reasons why people have suggested that you have flat slab subduction there in the past in the first place is that there might have been a thickened oceanic crust. Maybe basically the counterpart, for example, of the Shatsky rise may have gone under North America. Is that idea completely opposite to what you're suggesting? Because if you have thickened oceanic crust, what happens when it actually goes below 50 kilometers?
Well, the subduction of the chassis conjugate is something I've been working on for a long time. I got him, so you'll find lots of opinions here. But no, it did subduct under California with this big wad of buoyant crust. And the question is, as it subducts, it does get into the eclogite stability field. You got to follow the temperature. Okay, it's cold against the base of North America. How long does it take till it gets to the standard number people take is 750 degrees to actually get over that kinetic barrier? And if you model that, it happens about when the chassis conjugate gets to Colorado. Right when these big basins start forming there, by the way, or some of them. And right now, I would argue, I can pull up someplace, that the chassis conjugate is currently stopped under Wyoming. Okay, go through Xenoliths, I go seismic imaging, all sorts of things. So no, I really believe in that story. And it subducted as basalt, and it took a long time before it actually eclogized. In this case, that's why I think it's probably basalt under Washington. And it doesn't eclogize until the Yellowstone plume hits it and warms it up.
I probably don't know enough about eclogite. From what I've seen in a field project is when at the surface, I mean, basically garnet anthracite, that it also requires the presence of water to make that transition. And so I was wondering also if it's maybe not ubiquitous and just dependent on PT, but perhaps also on for example,
water is an agent that really accelerates it. Yeah. If you want. If you put dry eclogite in the eclogite stability field and warm it up enough, it will go anyway. But water really accelerates the whole process.
All right, I got a question for a little bit further to the west. So you're talking about the series of diking structures that generated that history of flows. And I got a little confused about the argument. It looks like the flows are keep stepping north, which seems to require either a continual welt of uplift or a tilting. And then you mentioned lateral flow mechanisms. Could you explain that?
Yeah, two things. I think the south to north propagation of uplift is perpetually damming the CRBs, so they keep flowing to the north. Okay, they can't get to the south. That's at 16 million years ago, roughly. Okay, then the CRB ends 16 million years ago, roughly. Now wait a few million years, so maybe 10, 11 million years ago. Now the Wallowa root seems to be coming off. We see it in the formation of the basins. We see it in some of the uplift evidence, and some of the very last CRB flows that just dribbling out amount of 2%. Well, less than those lateral. That's when the crust is, I imagine, radially flowing into this hole that's been evacuated, forming the circular bullseye structure. So two separate events related by the removal of the oceanic slab.
Any students or postdocs with questions?
Thank you very much. Very interesting story. Mark, I have a question. So from the general mental dynamic point of view, how a subducting slab can cause the upwelling of the mantle?
Okay, what I'm imagining is a slab at 50 million years ago was flat under that area. Okay, it already flat slab subduction, so it's there beneath Eastern Oregon and everywhere else. Okay, and then from 54 million years on, most of it comes off. guys look at where the volcanism is occurring and say there's no slab there. Okay, but under Eastern Oregon, that slab is still flat against North America. Okay, what I'm imagining is when it comes off, it's not subducting, when it's coming off, it's delaminating, pulling Yellowstone north. Or you could say Yellowstone is buoyantly pushing itself north. Both are going on, but it's not subducting, it's delaminating way late, 50 million years, 40 million years after its emplacement.
Great, thank you. But there's a requirement. You need a hot spot. You need a like Yellowstone, like a mantle plume. But what if you don't have? How can a slab cause the upwelling?
Yeah, yeah. How does the slab come off elsewhere? Is that, I don't know. There's more of the story in Washington, Oregon than I said, I have to admit. But it looks like the slab, looking for the volcanism, the slab came off in most places. I think underneath Montana and Idaho, it seemed to have come off and formed that curtain that I passed by. So that's another story. Okay. But it came off, and as it came off, you see these big volcanic events, Serica, the chalice, all that stuff. Okay. And why it came off and what triggered its delamination, I don't know. You look at Oregon and Washington, Oregon and Washington are about half their current width, or maybe 2/3 of it. And since 50 million years, they've expanded a lot with this extension. Okay, so a lot of what you see is Oregon and Washington maybe extending, giving rise to volcanism in some way.
Thank you.
Okay. But in a way, I like to turn it around. I look at the evidence where there's magmatism, the slab has come off. Okay. Even if I don't have a very good explanation for how it came off, it came off. Okay. Now it's our job to figure out what happened.
I guess following on the last two questions a little bit. So this idea of the ignimbrite sort of period, you have this, if I understand correctly, you have this sort of remnant flat slab that's in the area where the CRBs then come out.
Yes.
So I guess I'm wondering if you have any thoughts about the kind of cause and effect there. I mean, is the idea that the plume is holding it up and that's the one spot that you haven't lost the slab? Like, why is that the spot where it's still there?
My sense is, to get my perspective right, but that slab that I blew by in beneath Idaho now, that's what delaminated underneath Montana and parts of Idaho. You follow that up, it actually goes around underneath eastern Washington and Oregon. So that's one feature in a sense. You go west of that, and it's all been volcanically active, and all this extension and whatever you want. But it was just left there. Yellowstone just happened to come up just south of this area. I think it's just coincidence or coincidence, maybe. Yeah. Yeah, and I can say more about why exactly where, but I don't think, Yellowstone didn't hold the slab up. There, a lot of people would say Yellowstone actually hit in a little different place than just simple back projection and flowed up to where the lithosphere was thinnest. So and you can make stories, but the association with the southern end of the slab and where Yellowstone arrived, take to be coincidence.
So kind of asking the same question again a little bit, right? I mean, so I also wonder what role you attribute to the plume. And I'm actually very sympathetic to the plume messing with the slab. We've worked a little bit on this, but in terms of a flat slab scenario, as you've shown, right, there's all kinds of ways to make a slab go flat. It doesn't have to be a buoyant plateau. It can be sucked up by a cratonic keel, and that's all good. But what seems to be a little bit more difficult is to make the flat slab go straight again. And I wonder, you seem to say that you do think that the plume helped with that steepening part. Is that correct?
Several things to say. I think flat slabs are fun to talk about in their own right, but it went flat. Okay, I think it came off underneath Montana and parts of Idaho as it delaminated. Maybe it finally sat around long enough for the crust to eclogize. I don't know. There is also other volcanism there that, but the detachment for Eastern Oregon, once you have Yellowstone arrive, you have relative buoyancy contrast increase, you have melt to detach that The slab being dense compared to the crust makes relative tension right where you want to put the melt. Okay, so I think the Yellowstone's role is in triggering and enabling this delamination by detaching it with the melt and by ecologizing the crust so you have a load. Okay, so it plays an
What
important.
is important.
It is important. I don't think what we saw wouldn't have happened 16 million years ago without Yellowstone. It may have eventually come off. I don't know. But this story does need Yellowstone.
Thank you. Area with spectacular Earth processes 16 million years ago. Fast forward 13 million more years and more spectacular Earth processes. Many people know the Columbia flood basalts because of the Columbia River Gorge, which we think is carved out by these repeated glacial outburst floods from the melting Laurentide ice sheet. Is this geographic coincidence, or is there something about the changes in topography, the changes in Earth structure that you've mentioned that might might make this area susceptible to the creation of big meltwater lakes?
I wish I understood the gorge better, but the CRBs erupted 16 million years ago and flowed through the gorge. The cascades were already active well established since 35 million years ago. So there was a gorge there. A flow would go through and then get eroded out. The next flow would be next to it, but that gorge was always there. And it looks like it was always the locus of a stream going through to do the erosion. It's the only place I know of, and I've heard people say that it's the only place that they know of in the world where a volcanic arc has had a river go through it and maintain itself. So it's unusual that way, but it looks like it was always a drainage system there.
Thank you.
Real quick, last zoom out question, I guess. So going back to the plume head question, you're saying that where Yellowstone did this 16 million years ago is not the initial plume head. It's at Yakutatsia, Silesia,
Yeah.
right? So what do you envision the process is that goes from the initial flood basalt that makes the oceanic plateaus to the 16 million year event? What happens in between?
So I would point to,
What goes in-
going back to Geisen Richards or Vic Camp's pictures, I think what gives the rise to a plume head of some sort is the accumulation of Yellowstone plume under the slab that isn't getting through until it does. Okay, but it's there's quite a bit of what would have been plume to the surface that you're now have this reservoir under the slab accumulating in some fashion.
I guess the amazing thing is the time scale then. If it's 54 or something million years when Yakutatsia, Silesia are born, it's a lot of million years later before this whole event happens.
Yeah, no, the timing works out about right. It's like up to 50 million years, and then you see a little bit of it in the coast ranges penetrating through, and then it turns quiet. At 20 to 30 million years, you have those adakites, okay, and high potassium basalts. Okay, then about 16 or 17 million years ago, by plate models, Yellowstone plume should have been a little east of where the initial eruptions come out, but near there. Okay, so I think, Camp and Wolf would say it erupted underneath the western snake of the plain, but then flowed up to where the lithosphere is thinner or something. But who knows? But it's a big blob. It could have been everywhere. But it's a timing wise, it's about right. It's in the right vicinity at the right time to do this. It appears not to have been active before 55. No real sign of that. In Yakutat, you can look for the oldest rocks for Silesia. I think they're about 54 million years old. Yeah.
I could tell that Constantino really wanted to throw the cube, so I thought I should ask the question. That was a really cool talk. How you early on you quoted Leo Tolstoy about unhappy slabs are all unhappy in their own way. The famous quote we all know from Anna Karenina, the geophysics novel. So I was wondering how unique is the Columbia River province and all these processes you just discussed? Are there other places where you have a plume interacting with the subducting slab, delamination, things like that happening? Is this all unique? Or
I asked that question myself to myself. you know, I look at the Siberian traps, you know, something Brad Hanger and then the Elkins worked on, and it looks there like this giant flood basalt, but no pre-eruptive uplift, and that the flood basalts covered these coal fields at sea levels. So the uplift story, the count traps, you know, first of all, I always worry a little bit when you expect uplift and you go out and you look for it. You might find things you interpret that way, but I wonder how much real evidence there is for significant pre-eruptive uplift. I haven't seen any. I haven't done an extensive search. As far as plume slab interaction, I would say Thorsten has considered this. He might know more of the global literature than I know about that.
You know, my previous student, Erin Heilman, who graduated a couple of years ago, she worked on the possibility of having plumes actually disrupt slab. And you know, so we were like, that's cool. Did it happen? Right. And so we came up with a couple of examples where maybe it did happen. But I think what is more ubiquitous are anomalies that look like plume-induced sort of hot things next to slabs, and they interact. Now, is it a slab that's being fragmented by other processes that just allows the plume to flow through, or is it the plume actually actively messing with the slab? That's a more difficult question to answer. And I think the former is more likely and more probable and more frequent than the latter, but I think the latter is not impossible. But in general, we do see a lot of places. South America is one at present. There's sort of this hole. There's like hot stuff in between. There are places in, you know, underneath China and Japan where it looks a little bit like that. So we see these interactions, but how sort of what's chicken and what's egg is a little bit trickier, but it's been suggested in several places.
Seems like it's bound to happen someplace in this big Earth through all this time. And you know, I mentioned what Vic Camp points to on all this as observables, but this Atticide trend. I don't know how unique that would be, but it's certainly a clue to focus on something, see if you can relate it to a hotspot. Like I said, did Yellowstone actually burst through the plate? You know, I've always not liked that idea, though I count the number of times I've been wrong about things. I guess the Farallon plate, or the Wanda-Fucal plate, had a tear about at the Oregon-Nevada border. Okay, and you got normal subduction north and flat still to the south of it. And that flat section is moving north with time. So it's possible that Yellowstone did not break through. The slab just kind of pulled north and opened up the window for it. I don't know. But you know, it's a plume is a focus point on a big slab. I found it remarkable that it could actually get through. It's only 100 or 200 degrees, and the slab is, you know, 0 to 1,000 degrees or more. It just seems like a real mismatch of a wrestling match. But here we see evidence for it. So
the younger the subducting plate, the more likely it is for that like disruption to happen. But I think the plume is interesting, right? As Gene said, if you place the plume and then you have melting, you can have a very strong lateral density contrast. And Gene has sort of argued that this led to the steepening of the original flat slab. But of course, that's also quite likely to have been important early in the Earth, maybe even to start subduction. Where you don't have subduction, you have plumes leading to huge eruptions, and then you have lateral density contrast and give you sort of a density moment to get stuff going. So plumes have been suggested to either indirectly or directly start subduction in the first place. So there might be this original link, but in the present day, when we think sort of about the Cenozoic kind of typical scenario, you know, there are places where they seem to talk to each other.
well, one point I wanted to sort of make also is when I think about how the Earth works, I think mechanically or physically, we're talking mostly about the top and bottom thermal boundary layers. I find it interesting here that we're seeing this strong interaction between the two. And when we think about this evolution compositionally, I think mostly on top, you know, we're talking about this process primarily of putting basalt into the crust and then remelting it. And it's exactly what we have evidence here. We're putting lots of basalt in the crust. I look back to Cretaceous root. It's come, you know, we finally recycled that and we just left ourselves with this granite on top. So we're seeing all these major Earth processes concentrated right in this area. Just kind of fun.
Thanks.
All right, so this was awesome. Thanks, thanks a lot again. Let's thank Gene. Yes, and so I guess we're now have our reception. So please join for the reception.